Paul Codd, CEO of Flexergy, who's going to join us right now and tell us a little bit about what Flexergy has been up to. A relatively new company, from what I understand. I think you celebrated 1 year not so long ago. So looking forward to hearing more. Paul, over to you.
Afternoon, everyone. Let's get my slides going. Okay, can you see that okay?
All good.
Great. Well, this presentation is fairly meta insofar as is looking at the hydrogen economy and some of the barriers to getting it to scale where hydrogen can be cheap enough to be a viable alternative to electrification in some use cases, such as for heavy-duty vehicles, trains, marine transportation, anything larger than an SUV. We think that hydrogen could be a lighter weight and longer range, more powerful alternative. But generally, where electrification can be viable and economical, then that's generally the right answer. However, in order to get to true decarbonization, hydrogen is the next best alternative to electrification in most cases. So as I say, it's quite a meta presentation looking at Flexergy, the company, and we are a new start, 1 year old, as Dan says. So we'll look at the technology that we're offering, but also some of the dynamics of the hydrogen economy and what will bring those prices down and how we feel we're responding to that. So we are technology agnostic insofar as we don't mind how the hydrogen is created, what kind of electrolyzers are used, and so on. And we're agnostic as to how it's used. So whether that's for transportation or whether it's for other purposes such as chemical feedstock or creating green fertilizers. However, clearly it's highly relevant in the transportation sector. So we produce ultra efficient technology and products. That's always one of these ones that's okay, it's efficient, that's great, but who cares? Well, in fact, the Industrial Revolution didn't happen until James Watt improved the efficiency of the steam engine. So it can be one of those things that he didn't create the steam engine, he created the efficient steam engine. And that efficiency can be a catalyzing and cascading kind of effect where it can create a game-changing change of circumstances. So Flexergy does gas compression, storage, and transference. So in the bottom there, you can see we're looking at from renewable generation through to generating hydrogen in an electrolyzer. I'm just going to move this out of the way so I can see my own slides. There we go. Once it's generated, we need to compress and store that hydrogen in bulk. It then may need shipped to another location. There could be local transportation and local storage, perhaps on a customer site, and then the final use case, whether that's for refueling. So we're working with a bunch of partners that you can see the types of organizations we're working with up above. So we've got some really first-class people on board, working with some wonderful collaborators in our board of directors, people with experience in 50 years experience in one case. In hydrogen, there can be only a couple of dozen people in the world that can claim that, probably. So yeah, we're really excited about how we're going to be taking this company forward. So one of the problems with hydrogen is that when you create it, every time you move it through this value chain from compression, storage, shipping, tube trailer, vehicle refueling infrastructure. Every time you move from one part of the system to another, it can have a pressure drop. You can create turbulence in the gas that can change the temperature, and all of these things lose energy. So we have a way essentially of doing that, those transfers without those losses. And we're working in that middle part of the value chain. So there's been a lot of work and research and a lot of companies there in that sort of electrolysis stage, or renewable generators electrolysis, and many companies looking at the final use case, whether that's fuel cells or vehicle charging, refueling infrastructure, but a lack of attention in that middle piece of how you get the hydrogen from where it's produced to where it's needed. And clearly that's a critical piece of infrastructure. So looking briefly at Scotland, I appreciate this is, again, this is a little bit meta, but and a lot of the renewable resource is coming from offshore wind in terms of how we take things forward in future. But the demand centers for where hydrogen is needed are not necessarily where the renewables are located. So the task in hand is getting it from where the hydrogen is being produced, which is, and there are projects in all around Scotland, typically at the coasts where onshore wind makes landfall. And as an example of that, ScotWind, sorry, is now 28 gigawatts projected production, but in fact, it's not able to put even probably half of that electricity into the current electricity grid. Even with the projected infrastructure increases, they will not be able to inject that electricity into the grid. The infrastructure is not there to be able to accept it. So they will need to turn that into hydrogen in order to create, to deliver that value to customers. And those customers are going to be located all over the place in Scotland, England, and in Europe. So how do we transfer it from where it's created to where it's needed? So we've got a number of options for doing that. Clearly the electricity grid is one of them, but also liquid hydrogen, pipelines, and ammonia. So in terms of the electricity grid, there are a number of pros and cons which we can look at. So it already exists. There are plans to upgrade it, and demand for electricity is set to increase. It's going to be a very important way of moving energy around. But existing grids are already very constrained. Anyone that's trying to get renewables consented, it's finding it very difficult. If you have a very large demand center, whether that's for charging a fleet of vehicles or something like that, it's also very difficult to get that congested, but it's very site specific. It depends on the grid in your area. They are looking at upgrading the grid, but the 10 gigawatts of capacity that they're looking at increasing in Scotland by 2030, 9 gigawatts of onshore wind are waiting to be consented. Sorry, have their consent, but don't have grid connections, are waiting to accept most of that new capacity. So there's a structural shortfall there, and the grid has typically not considered energy storage sufficiently, in my view. It's relied on essentially burning a gas peaker plant somewhere to create a bit of extra energy, or to flex that demand up and down to meet the demands as they change. So energy storage is not really built into the grid in any kind of sufficient way. Some people say there are 1,000 times more energy stored in fossil fuels in our energy system than there is in all of the hydropower and battery packs added together. So pipelines are another way to move hydrogen around. They are very often the cheapest way to move from point A to point B, but they are extremely expensive to build. It can take a very long time to have them designed, permitted, and constructed. And then once they're there, they're inflexible in terms of you can't just suddenly route that hydrogen to another place. It's once it's going in a particular direction, that's all you've got. Liquid hydrogen, it's very energy dense. You've got reasonably low environmental impacts. And some end uses require liquefied H2. I know that some trucks are looking at that as a potential fuel source, and other vehicles. But you need to get down to almost 0 degrees, absolute zero. It's minus 253 degrees or something like that. It's very, very energy intensive to create liquid hydrogen and then to keep it as a liquid. And it takes a refinery, essentially, something of the kind of scale up like Grangemouth to create and then deliver that into a distribution infrastructure such as ships. Ammonia, similarly, it's very energy dense. There is an existing supply chain, and it has some uses for making green fertilizer, for example. But you need to reach 600 degrees in the Haber-Bosch process to create ammonia. So it's also very energy intensive and therefore expensive to make ammonia. And similarly, you need large scale refinery style infrastructure. So Flexergy is creating a different way of doing this, which is much more energy efficient. We're keeping it as compressed gas. And that, because of our efficiencies, we can actually lead to 20 to 40% lower shipping costs, particularly in the higher end, the 40% is where you're looking at tube trailer distribution, very relevant for fleets. And it has a lower environmental life cycle. So essentially, those efficiencies mean you get more hydrogen delivered for the same amount of renewable energy. And very importantly, you need a smaller project size in order to make that viable. So whereas with a pipeline, you need to be shipping 30,000 tons of hydrogen per annum in order to make a large-scale pipeline viable, or a large number with a carrier. With compressed gas, that number can be brought right down, which means that you can scale hydrogen production facilities in line with commercial milestones, rather than having to make these cliff edge investment decisions. And it's much quicker to permit, to design, to build, to get it operational. So in summary, that means we've got more projects viable sooner, we've got cheaper hydrogen, we've got less inventory in the system, less land use, and we can use existing ports with minimal infrastructure rather than waiting for these big refineries to get built. So looking at from a product development point of view, we're developing a compressor and storage system at the minute. We're hoping to have a pilot operational in 2023, and then to be in mass manufacture in 24-25. We're looking at installing this technology into a tube trailer system. We're wanting to pilot that in 23 and to have that pilot operational in 2024, or to in fact have a number of pilots operational in 24, and then move into mass manufacture in 25-26. And the flagship product, if you like, is a marine carrier vessel. That's a much more ambitious project and has a longer time scale. But again, we're looking at piloting in 25-26 and moving into mass manufacture in 27-28. Now, these are smaller ships than the very large, refinery scale ones. So we're looking at creating, a large number of these ships and having them rolling off of the production line, hopefully on the Clyde, but yeah, who knows have a large number of these entering into service from 27-28 onwards. So I was asked, what is my ask? Well, I suppose all projects need money, so we're looking at raising a number of investment rounds. There's a pre-seed round we'll be opening this year, and that will lead quickly into a seed round in the following year. And that's it. Thank you very much.